Yeah, one moment. I'm just putting it live on YouTube live stream. Then you can join.
Yeah, sure.
Yeah, you can start.
Okay, sure, I'll start.
But I have to make you co-host. That's just. Yeah, it's been recorded anyway. So there are two people here. Who?
And Dhruv.
Yeah, why don't you come sit? Well, you can watch from there. I think you can. You're Drupjyoti, na?
Yes, Dhruv.
And
Ashutosh.
Ashutosh. Drupjyoti and Ashutosh are here. I think you should start because it's been 5. I think a Kauri, Shauriyam. He might be joining, but nonetheless, you should finish it off.
Yeah, usually Soham is also here.
Are actually busy with the placement.
Oh, I see. Okay, go ahead. Yeah.
Okay, sure. All right, so last time we were looking at LynSim and we sort of give a high-level picture where the idea is that you'll pass or whatever deep poly-like algorithm there is.
Let's distort.
Hello.
No, go ahead. Sorry for the disturbance. Yeah.
Okay, sure. So whatever deep poly-like algorithm there is, it'll give you what activation function there is. It'll give you some concrete lower and upper bounds. And then LynSim is supposed to automatically calculate these linear upper and lower bounds for your function, right? So for example, if you have, this is your activation function, then deep poly, so if this is the activation function, deep poly will give you these lower and upper bounds, and then LynSim will return these linear bounds for the function within this interval automatically, right? And we also say that at a high level, this happens, or LynSim does this by using 2 phases. In the first phase, it will use a bunch of samples on the activation function to get a rough estimate of a good slope. And while it's finding the slope, it's going to minimize the volume, right? So it's going to find a slope that, or find a line so that it's not below any of these samples. So it's going to find a line whose slope is such that it doesn't pass below any of these samples. So a line like this would not be allowed. And it's also going to find among all of those lines, the one which maximizes the volume below it, right? So here I'm only talking about the upper bound. When we go to the lower bound, it will be like the volume above it, but it's basically symmetrical both ways. So it's going to take all of these samples and it's going to try and find a line that passes below it and maximizes the volume while it does that, right? So that's the first phase. And then in the second phase, it's going to check whether this line actually is a linear upper bound for the activation function. If it's not, for example, in this case, it's not, right? There is a small region in which it violates the fact that it's an upper bound. Then it will try to find the minimum shift it needs to do and to try and shift it upwards so that it is actually becomes sound. So in this phase, it will basically apply a small shift, try it. If it's still not satisfied, increase the shift a little bit more, try again, and so on until it it basically becomes a proper upper bound, right? So in this phase, it sort of iterates on the shift.
Yeah, Diganta.
Yeah.
So in this case, linear upper bound. So in general, you'll have to have, in 2-dimensional linear upper bound and lower bound. Or in general, if it's multi-dimensional, you have to have some kind of I guess several planes intersecting that will a polyhedral something, you know, cone.
No, it'll just be a single plane, even in that case. So I'll draw a picture. I'll draw a picture for, say, when we have, say, when the activation function is, say, R2 to R, right? So let's say that the activation function takes.
நான் 6 மணி சொன்னேன், 5 மணி சொல்லலையே, 6 மணி சொன்னேன். Okay, sorry.
Yeah, so suppose that we have a situation where we have an activation function sigma that is taking 2 real variables to 1 real variable, something like, say, multiplication will fit this sort of a situation. So then if we want to draw it, it's going to look like this, right? So these are the 2 input variables, let's say x1 and x2. And you have the output variable y. And then the actual activation function is some surface, right? So maybe it's some surface like this. Right?
Yeah, because it's always producing a single output. Correct.
Right.
You're looking at the output of a single node.
Yeah. So activation functions in general in this case are considered as Rn to R functions.
Okay.
So it will be a plane. Yeah.
At all the entire layer. Okay, so fine.
No, yeah. So then you might take some samples like this and such things, and then the linear upper bound or lower bound that you would get is going to be a plane. So again we'll have an interval. So we'll have some bounds on x2 and some bounds on x1, and that gives us some interval within which we are interested. So some interval like this, which will basically be a box in the x1, x2 plane. Right? And within this box, we're looking for, and it's a little bit hard to draw, but like we're looking for a plane that is always above this surface, and it's tight. Right?
What is the box? I didn't get, what is the box supposed to signify?
The box is the interval within which this x1 and x2 lies. So x1 lies in some a comma b, ax comma bx, let's say. Yeah. And x2 is in some ay comma by. Or something like that. So then this will be sort of ax.
Yeah, you will have 2 lines, I guess, no?
Yeah, we will have a box of x1, x2 values within which you're interested, and inside that box, a plane should be an upper bound for the curve. So in this case, basically, sort of this point is ax, the lower bound of x and the upper bound of x2. So ax comma by, this point is going to be bx comma by, this point is going to be bx comma ay, and this point is, this corner is going to be ax comma ay. Right? So those are the corners of the box. It's just like in an interval domain, what you get if you say this and this holds, you get like x1, x2 values belong to some box, some rectangle, right? So that is all that I've drawn. And then within that, this blue plane, this light blue plane should be bound for the dark blue curve. So this light blue plane that we have, this should be a bound for the dark blue curve. That is what it will provide. Is this okay?
You understand?
Yeah. Okay. So one of the important sort of observations that these guys made, which led them to split this algorithm into 2 phases, is that the slope of whatever plane or line that we come up with, the slope of the line and the shift, or the actual constant term in the expression, the shift of the line are independent. Right? And what they mean by that is, see, if you have a line that is, if you fix the slope, then you can always find the minimum shift that works for that particular slope, right? And if you have fixed the shift, then you can always find the best possible slope that you can find with it, right? So once you fix the slope, then you can find the shift independently of it, or once you fix the shift, you can find the slope independently. So what they choose to do is they choose to fix the slope, and then for that slope, they'll find the best possible shift. So it's like the slope and shift, they don't have to search for all possible slopes and shifts together. They can just find the best possible slope first and then worry about the shift. Because for each sort of slope, you will have a best possible shift, right? So if I say that, okay, my line is going to be parallel to this, if I fix the slope to be something like this, then I know that the best possible shift is going to be one that is going to let the line end up somewhere over here, right? So once you fix the slope, you have the best possible shift is automatically fixed for you. So they firstly worry about the slope in the first phase, and then later on they separately worry about the shift. So in that way, they're able to worry about them independently as opposed to having to optimize both the slope and the shift together. Okay. So now let's go into the details of these phases. So this is the details of phase 1. And in phase 1, remember what they're trying to do is they're trying to find the slope.
Question. I'm sure the details are probably there in the paper.
Mm-hmm.
Even the first phase, the first unsound bound. Okay?
Mm-hmm.
How does it find? I mean, it has to, there are several parameters that it has to find, the coefficients.
Yeah. And so that is basically the phase 1 of the algorithm, finding this unsound bound, which is.
I'm asking. I'm trying to get some insight, quick, as to how it's an optimization problem.
So okay, so maybe let me just draw some pictures.
Reduce the volume. That is okay, but still it has to do. Oh, so it's an optimization. So it has to find the best fit for all the coefficients,
such that the volume is minimum and it is above all of the samples. So I'm actually going to explain just this very thing in detail right now in this slide. So
okay,
yeah. So basically the first step in finding this first like rough estimate where they only care about, or the first unsound bound where they only care about the slope, which is done in phase 1. So we're talking about phase 1 right now. The first step is it's going to sample the input intervals uniformly, right? So what that means is that, suppose this is the picture that we're working with. We have, this is our picture, let's say, and that suppose this is the region in which we're interested. And let's suppose that the activation function looks something like this, right? So the first step is going to be that they're going to find, they're going to sample this uniformly. So they're going to sample this interval uniformly and get a number of samples over here. So 1, 2, 3, maybe let me just do a few samples only. So some large number of uniform samples. And again, this number of samples is something that you can tweak, but they say that going with something like 100 samples initially is a good idea. And then for each one of them, you're going to just evaluate the activation function to get the points along this curve at a regular interval within your within the domain of interest, right? So we're going to get some points like this. So this is the first step, which is to sample the curve in this way. So now, what do we know about, now we can phrase things as an optimization problem, right? So what do we know about the plane that we come up with? The plane should not ever be below the samples, right? They should not be below the samples that we have found. So what does that look like in terms of a symbolic set of constraints, right? So let's write it out. So basically, your plane is going to be given by something like this, right? So your plane is given by y, or your plane equation is given by y is equal to summation over ci xi plus c naught, right? Where xi's are your inputs and y is the output of the activation function. So activation function sig is given by sigma of xi. So sigma of, let's say, x1, x2, up till something. And that I'm calling as y, right? So the plane is basically going to be given to y is some summation of this ci xi and plus c naught. And what we're looking to find is these ci's and C naughts, right? So we're looking to find these and this, correct? So now what we know is that we know that at each one of these sample points, this plane should be above, right? So what does that tell us? So each one of the sample points, remember, we can call these the samples in the input interval as SIs. Let's say that this is S1, S2, S3, S4, and S5. And for each one of them, so let me just make sure that I'm keeping the notation same. Yeah. So for each one of them, we have over here, the value over here, the value of the activation function is going to be some sigma S1, sigma S2, sigma S3, sigma S4. And let's just call these things some different name variable names. Let's call them Ys, because these are again found just by evaluating the activation function, right? So let's call them Y1, Y2, Y3, Y4, Y5, where we know that Yi is just sigma of Si. And we can find this just by evaluating sigma at a single point, right? So now what we know is that this plane that we're trying to find, this should be above each one of these sample points, right? So what does that mean? That means that if we evaluate the value of Y according to this plane here, then what we should get should be above each one of these Y3s, right? So for the first sample point, we'll get, sorry. For the first sample point, we get sum over I, Ci, Si, right? Sorry, let's say S1I, right? Because remember that in general, the first sample point is going to be just some vector, right? So let's say the notation is something like this, right? Because again, if you go to the 2D picture, then the first sample point is going to be some 2D point over here. So if this is the first sample point, if this is S1, it's going to look like some S11, S12, right? Okay, so we have this, and this is the first sample point, and we know that the plane should be above. So the equation of the plane is this plus C naught, and it should be above whatever value we get, right? So that means that it should be above Y1, right? So for S, the sample point 1, we get this. In general, for sample point I, we get sum over I, Ci, Si, or let's say sum over J, Cj, Sij, plus C naught should be greater than equal to Yi, right? And we know that all of these things should hold. So the set of constraints on our plane, which should translate to a set of constraints on these Ci and C naught, it is just a conjunction of these constraints. And notice that each one of these constraints is a linear constraint, right? So at the end of the day, we have a conjunction of linear constraints, right? So we have a conjunction of linear constraints, each constraint looking like something like this. Right? So just to make things a little bit more concrete, I'll maybe.
But one thing, see,
yeah.
there are linear constraints, all right, but here the Sij's are known, but the Cj is not known.
Right. So this is a set of linear constraints.
It is so those are the n variables, so you have to solve for those variables.
Right. Yeah. So here we are solving. Here we know Sij, and we also know Yi, because Yi we can just evaluate the activation function at a point to get them, and we solve or we find Ci and C naught, right?
Yeah, but where is the volume reduction constraint here?
So there is no volume reduction constraint. So far we have only characterized the set of allowed constraints. So far we know what the constraints on Ci should be, and now within these constraints we should reduce the volume, right? So far we only have the set of constraints, we don't have the objective. So this gives us the set of constraints. And the volume reduction condition will give us the objective. Right? So just to make things a little bit more concrete, I'm just gonna maybe show explicitly what the situation will be in the 2D case, right? So in the 2D case, remember that our line is just a plane. So we are here doing the 2D case, right? So in the 2D case, our line is just a plane and it's given by y is equal to mx plus c. Here we need to find m and c, or maybe I'll just call it c1x plus c0, just c1 and c0, right? And now what we know for that whatever the line is, for each point, the line should be above this S1, Y1 point, right? So whatever the line is, it should be above the S1, Y1 point, it should be above the S2, Y2 point, S3, Y3, S4, Y4, and S5, Y5, right? So since we know that, what we'll know is that Y1 should be less than C1, S1 plus C0. And Y1 should be less than, Y2 similarly should be less than C2, S2 plus C0. Because remember, this point here is given by S2 in the X coordinate and C2, X2 plus C0 in the Y coordinate, right? And we're saying that this should be greater than the Y2 value that we have. So Y2 should be greater than, or should be less than C2S2 plus C0. And similarly, we'll have Y3 and less than C3S3 plus C0, and so on until Y5 is less than C5. Sorry, so these are all C1s. It's not C2.
Yeah, you just rewritten the same thing that you had on the right side.
Yeah.
Case of two variables. That's all. Okay.
Right. Yeah. I just thought that will be a little bit helpful, but okay. Yes. Okay. So far we have the set of allowed values of CIs and CJs. We have expressed that as a conjunction of linear constraints, right? So here we have point number 1. The set of allowed values of CIs and CJs is a conjunction of linear constraints, right? And it looks something like this. These give us the allowed values. Right? So now the second step is how do we actually express the minimization of volume, right? So let's see how we might be able to do that. So again, I'm going to, let me go to a new page and let me copy that diagram I had. Right? So again, let's look at the 2D case for a second, right? So in the 2D case, again, we know that so again, in the 2D case, we know that y is equal to C1x plus C0, right? And then the objective, if we remember, this objective was this volume, right? And the volume is given by going from L to U, this integral of this y, right? So the integral of C1x plus C0 dx, right? If you remember, this is the volume, right? So the volume is just going to be the sort of the area under the line, or the space under the line, and that space under the line within these bounds is going to be given by this sort of an integral, right? This space is going to be just given by this integral, right? So far, is everything okay? I should have probably stopped when I had the objective function written as a conjunction of constraints, linear constraints. This is okay, right? The fact that the objective is a conjunction of linear constraints. Sorry, the allowed set of values is given by conjunction of linear constraints. Any questions at all so far?
Fine.
Okay. So yeah, so now let's talk about this volume, right? So this volume is given by this integral. So let's see if we can simplify this integral, right? So remember, this is just a linear integral, correct? So since this is a linear integral, this is given by C1 times U minus L plus, so integral of x is basically going to be what? So it's going to be C1x squared by 2 U L plus C naught U minus L, right? And this is going to be C1 L squared, sorry, U squared minus L squared by 2 plus C naught U minus L, right? So notice something, that this is also linear in C1 and C naught, right? So these coefficients are complicated, but these coefficients are in terms of U and L are something that we know. We can just calculate them, right? So this turns out to be linear in C1 and C0, correct? And this is slightly more complicated calculation, but this actually is true even in the more general case. So let's do the 3D case where we have 2 inputs to activation function. So let's say that we have the 3D case. Sigma is going from R2 to R. Previously, we had sigma going from R to R, right? This sigma is going from R to R case. So sigma is going from R2 to R. We also have the same sort of a situation, right? So their volume is given by these set of 2 nested integrals, right? So we'll have going from L1 to U1 and again going from L2 to U2. And again, we'll have C1 x1 plus C2 x2 plus C0 dx1 or dx2 dx1, right? So again, if we evaluate this central integral, what do we get? We get integral from L1 to LU1. And here we get, we will basically get C1 x1 U2 minus L2 plus C2 U2 squared minus L2 squared by 2 plus C0 U2 minus L2, right? And now we can expand the outer integral or evaluate the outer integral. And again, we will get C1 U1 squared minus L1 squared by 2 times U2 minus L2 plus C2 U2 squared minus L2 squared by 2 times U1 minus L1 plus C0 U2 minus L2 times U1 minus L1, right? And again, notice that this, although looks very complicated, it's linear, right? These things, this is just some constant that we know. It's just an expression involving U1, L1, U2, L2. So it's just some constant that we know. This is again some constant that we know. And this is also some constant that we know. So at the end of the day, this entire thing again is linear in C1, C2, C0, right? So is everybody following these calculations?
Yeah.
Yeah. So in general, if you have any sort of an expression that looks like this, in general, your volume is going to look like integral from, U1, L1 up till, let's say, integral from U, K, L, K. And then you're going to have C1, X1, CKXK plus C0 DXK, DXK minus 1 up till DX1, right? And again, what we can do is we can evaluate the innermost integral and we'll get something linear, right? Linear in terms of C1, C2, and so on. Then you can sort of use an induction hypothesis and prove by induction. And I'm not going to go through the steps of this unless you want me to, but I think it should be easy enough. So you can prove by induction that the above is linear in Ci, comma C naught. Okay. So is everybody at least intuitively seeing the fact that this should be linear in Ci, comma C naught? Like if you evaluate, let's say the inner, if you have an induction hypothesis, what you can do is you can use that to evaluate the inner k-1 most integrals, right? So then you'll have one integral of something that is in one variable and is linear. And then if you evaluate that, you'll again get back something that is in general linear, right? Yeah. And what I want you to do maybe as an exercise is prove that this integral, which is what I had, which is the general volume expression, this evaluates to this. And you can do this by induction. You can show that this will obviously or very directly be true for the case where you have only one with a number of such, with D is basically one. So here they're taking D as the number of constraints or the number of inputs to the activation function. So if D is one, this will very directly, you can show this to be true. It's just a single integral. And then you can use inductions on the inner D-1 integrals over here. And then evaluate the outermost integral and you will find this expression, this precise expression, right? So can you guys do this? Or do you want me to do this? Is this okay?
I think that should be enough. Yeah, because
so
stop 6, therefore I think they should that's good to be left as an exercise. I think it's conceptually it's clear now.
Yeah. And it's just a lot like some calculations, just evaluating some integrals and very direct application of induction. There's no trick or anything involved. But what I do want to point out is that, see, now we have a very interesting situation, right? We have a situation where the allowed set of constraints, so we have two things we know, right? So the allowed set of constraints is a conjunction of linear constraints, right? So the allowed values are a conjunction of linear constraints. And the volume is a linear expression, right? So we're trying to minimize this which is linear in the CIs and C0 and all of that, subject to this. Right? And this is precisely a linear optimization problem. You have a bunch of linear constraints that you have to satisfy, and you're trying to minimize a linear objective function. So what they have done is they have this initial finding a good enough line that might be unsound, but still at least is sound at these sampled points, that actually reduces to a LP problem, a linear optimization problem. And then they say that they're going to solve this using an LP solver. Is this clear to everyone?
Yeah.
So that's it. This is phase 1 is just using an LP solver, right? And I just want to point out something, just an aside for people who are aware of things like convex hull sort of operations. This is very close to a convex hull operation, but it's only worried about the volume in one sort of direction. So in that sense, it turns out to be simpler and can be done with one LP call, right? So what they're actually doing is they have just some number of sample points here, right? and they're just trying to find a line which is above this and minimizes this volume. This is kind of like finding a single constraint for, you know, a region or a single side of a convex hull of a region that is given by these points and is joined with this axis, right? So if I tell you that, okay, whatever, you know, the hull of this region is, it's going to have just one side, then the optimization problem that you'll get is precisely this. So all they're doing is they're just taking this line and sort of trying to find the best possible line. And you can also sort of imagine it as what would happen if you were to drop a line. So if you imagine if you were to drop a line on this and just let it fall according to gravity, it will just settle along here, right? It will be perched on each one of these things, and it will be perched so that the volume is maximized, right? So these are two ways that I thought, like, you know, thinking about this might be helpful. One is that it is basically a sort of a restricted convex hull sort of operation. And the other is that like it's like you're visually, it's basically you're just dropping a line and slowly lowering it, and you're getting the best possible thing. But of course, what they're actually doing is phrasing it as an LP problem and passing it to an LP solver, right? So this is the important thing that one should keep in mind. So any questions so far regarding phase one? Then if not, I'll move on to phase two. Okay, so I guess I'll move on.
The more points you have
Hmm.
your sample set,
Yeah. The more you know,
variables will be there in which you have to for the LP solver.
No, so the more points I have, the more constraints there will be there. The number of variables, and maybe I should make this clear.
No, but the more points you have, the more coefficients will also be there. No?
No. So if
Coefficients will correspond to the dimensions.
so, the coefficients will correspond to the number of variables. The coefficients are the number of variables, and the points are the number of constraints. So each point.
Yeah, there'll be more constraints. You're right.
Yeah. So each point.
Yeah, got it. Okay,
Yeah,
I don't
sure.
think
Sure. Okay. So maybe So the size of this LP query is basically number of points into number of dimensions, right? And the number of dimensions is basically the number of variables you'll have. Number of points is the number of constraints that you'll have. So this is, I think this is a good thing to keep in mind in terms of, you know, if this LP query becomes unwieldy, then maybe you can do less number of samples, then you'll have less number of coefficients and so on. Right.
Because the complexity of whatever simplex and things like that is also depends on the number of constraints.
Yes. It is dependent on both the number of constraints and the number of variables. So number of variables is something that you can't control, right? It's just the number of inputs to the activation function, but you can reduce the number of points by making the sampling sparser. But if you have a more sparse sampling, that also means that your initial guess will be more, you know, it will be worse, right?
I'm sorry, yes. More sample points means it will be better.
Yeah, the initial guess will be better. And that will mean that the algorithm will perform better in phase two. And it will also might mean that the line that you'll get will be tighter, right? So the tightness or the quality of the line depends on the number of points. So there is a trade-off over here. So more points means better bounds and potentially faster phase two, but it also will mean that phase one and the LP solver will take a long time. Okay, so now let's go on to phase two. Right. So phase two is finding the shift. And again, this is phase two, right? So now what we want to see is we want to sort of minimize the global worst possible violation, right? So the violation is given by this. They define something called a violation function. And it is given by this sort of an expression. So see, what we have now is we have a plane that is given by y equal to sigma I xi ci plus c0. And we have an activation function sigma of x1 and so on, right? So let me just call it sigma of xi, right? And we want what the actual soundness condition that we want is that this plane should always be greater than or equal to this sigma, right? In other words, what we want is we want this expression to be always greater than or equal to 0. Right? And this expression, what they call this expression is called the violation function. They call this the violation function, and it's a function of Ci and C naught. And what they want is that this expression to be greater than or equal to 0 for all, sorry, so it's a violation is in terms of xi and x naught. And they want this violation function to be greater than or equal to 0 for all possible xi's and x naught, right? So the soundness condition is that for all xi, sorry, I don't know why I'm saying x naught over here. But what we want is that for all xi, this v of xi should be greater than or equal to 0, right? So now
you have to find a plane which at no point is, at every point it is sound, right?
Yeah, exactly. At every point it is sound. So now what they do is they again sort of have 3 phases in which they'll fix the shape. So at this point, they already have some guesses of this coefficient, C1, Ci's and C naughts, right? So at this point, they're only going to vary the shift, right? So they've already fixed Ci and they're not going to touch the Ci's anymore. They're only going to vary C naught. So in other words, they're only going to add some term delta to C naught, right? So now the part of this thing, the idea behind this phase is to find some delta so that this condition begins to hold, right? And again, what they do is they have some 2 sets of sort of heuristic-based approaches, and then finally they'll be using an LP solver, right? So the first one is, sorry, an SMT solver, not LP solver. So the first one is that they'll again do a sampling on the input domain, right? And this time they'll have a very large number of samples. And they're just going to pick a minimum value for the delta, right? So again, what they'll do is okay. Yeah. So again, remember that what we have is we have this violation function. Violation of xi is given by sigma ci xi plus c naught minus, sorry, yeah, this, right? And what they're trying to find is they're trying to find a delta so that sigma ci xi plus c naught plus delta minus this is greater than or equal to 0 for all xi, right? And again, so for all xi within some li ui. So they are, xi's are bounded within some interval. So now again, this particular thing, what this boils down to is this to find the minimum value of vxi, right? So if we know that vxi is actually greater than or equal to some delta or some minus delta, then, or let's call it minus d, let's say, then we can set delta to d, right? Because then what we'll know is that will mean that vxi plus d is greater than or equal to 0, and then this expression is going to just become vxi plus d, right? So is this clear to everyone?
Yeah.
Yeah. So now the first thing that they do is they'll again take a use. When this say use, they mean something of the order of 10 to the power 6 samples again, and find the minimum VXI within those samples, right? So because now notice that what we have is essentially another minimization problem where we're trying to basically minimize. So finding this minus D is the same as minimizing or find minimum value of VXI, right? So if you can find the minimum value of VXI, then we can just set delta to the negation of that and we'll be done, right? So is this clear that like right now finding the minimum value of VXI is going to be okay? So again, I can draw a quick picture. So in this sort of picture that we had, maybe I should draw a picture. Yeah. So we have this sort of situation. This is our activation function. This is the line that we have already found, right? And then this difference is basically our violation, right? So our violation is basically the value of the line minus the value of the activation function. So it's going to look something like, it's going to be negative here, or sorry, positive here. So it's going to look something like this, and it's going to dip below 0 here, right? And then the point where this is minimum is the point where the actual activation function is farthest from the line. And that is also the amount that we have to shift the line upwards to make things work out, right? So again, the situation is that we have to find the minimum value of this VXI. With this VXI is the difference between the line we have found and the actual activation function. Is this clear to everyone? Yeah. So, okay. So what they do is they again take a huge number of samples, some 10 to the power 6 or even more samples in the input domain and find the minimum value of VXI within those samples, right? So again, this will basically, in this particular picture, will correspond to taking a bunch of samples over here, a huge number of samples over here, take all the VXIs or evaluate the VXI at each one of these points, and then find the minimum of them, right? So that minimum that you'll get is already going to be very close to the global minimum, right? But it might not exactly be the global minimum. So in the step number 2, what they do is they'll use black box optimization. So something like is, gradient descent. Things like gradient descent. And here is where, your activation function needs to be differentiable almost everywhere, right? So remember VXI this is given by something linear minus activation function. So if this activation function is differentiable almost anywhere, this will be differentiable almost anywhere, and you're allowed to do gradient descent on it. So then what they do is they use gradient descent with, and so again, the minimum VXI, let's call this the XI star, with XI star as the starting point. Right? So remember what we had done is we had taken a huge number of samples and found the minimum among them, and that had actually gotten us close to the actual global minimum that we have, right? So we are kind of close to the actual global minimum, which is this yellow point here, but we're not exactly there. So then what they say is that, okay, then do gradient descent on this, and this will get us even closer, right? So is this second step also okay to everyone? Yeah. So now what we have is that we are at this particular point, and we're very, very close to the actual global minimum point, right? So that means the value of shift that we have is very, very close to the actual shift that will work. So now what they do is they'll basically So now we have a very good, we have a delta that almost works. And the first thing that they're going to do is pass it to an SMT solver. So we pass it through an SMT solver and check whether this delta works or not. We check whether the delta works. And if the delta works, then we're done. If not, we set delta to delta plus some really small value. So what they use is 10 to the power minus 6. And then they repeat. Right? And they'll keep doing this until finally they have a delta which passes the SMT solver check. And then, you know, we have, we know that we have a sound upper bound, right? So again, just to be sure, this SMT solver check basically is this. When I say do an SMT solver check, I mean check whether Vxi plus delta is always greater than equal to 0. Right, so you're going to negate this and pass it to the SMT solver. So you're going to pass to the SMT solver something like Vxi plus delta is less than 0. And if it gives sat, then that means that delta is not good. Otherwise, if it is unsat, then that means that delta is good. Correct? So is this okay so far?
Yeah.
All right. So far we have
Can I have 5 more minutes?
Yeah, sure. Five more minutes is going to be okay. So far we have you know, so what I want to point out is basically that this algorithm, what it does is it spends most of its time progressively getting better and better guesses for next algorithms, right? So it's like, firstly, it's phrasing this as an NP problem. That gives it some good guess. Then that is used as a guess for doing even more dense sampling to get a better delta. And that is used as initial guess for SGD. And the result of that is again used as an initial guess for this SMT solver based search algorithm, right? So they are basically taking more and more finer search algorithms and passing the best guesses from each search algorithm to the subsequent search algorithm, right? So that is basically the entire sort of idea behind their framework, where they'll take, you know, one coarse search, get something, pass it to a better, finer search, get something, pass it to an even more finer search, get something, and so on. And the search algorithm sort of chain that they have is something like LP going into sampling, going into SGD, and then finally going into SMT based search, right? So this is one thing that I wanted to say. So there is another sort of aspect to it which I haven't covered yet, and I don't know if I'll get time. But basically, they use a very special SMT solver. Maybe I can take just 2 minutes to cover this. See, the issue with using something like Z3 at this stage is twofold. One is that Z3 is not very efficient for the kind of queries that they end up with.
Why?
Or rather, let me put it this way, that there is more efficient solvers available. The solver that they use is, yeah.
So that was because, why? Because it is
non-linear.
Real.
No, I think it's what they sort of point out is that it's highly non-linear, right?
What is non-linear here?
Because the sigma is non-linear. So remember at this stage, so
yeah, there's minus sigma xi, no?
Right. So from anywhere, everywhere up until this point, they have to deal with the actual sigma. So SGD can deal with non-linear things very easily, right? Because as long as things are differentiable. But SMT solvers may not work. And in fact, they say that Z3 did not work because, especially for non-linear sigmas like tan H and things like that, or sorry, sigmoid and things like that. And secondly, is that
What do they use? I know there are solvers that are exclusive. I mean, they are built to handle nonlinearity.
yeah, and they say that using some solver that is directed for nonlinearity is going to be better.
You name it. I know one. The one called YICES, YICES,
Right.
has extensions that are exclusively made. And MathSat is another one.
Right. Yeah.
MathSat. I
So
don't know
what
which
they
one.
use though is something different, and they're sort of they. I think there's another reason why they use it, and I don't know if I'll be able to go into it, but they use something called DReal. So that is basically a branch and bound solver. It is meant purely for reals. It's not an SMT solver. It's a more like a decision procedure purely for real nonlinear arithmetic, and it just uses branching and bounding. And I'll go into it in some detail, but it is actually solves the relaxation of the SMT query. It's some sort of a
So
node
I think
approximation.
you have to end now here, except to say what what more do you have a plan to cover and
So I'll take maybe just 5 minutes of the next class, or
okay.
5 to 10 minutes. Okay.
Take more. I mean, what I'm thinking of doing is to kind of finish this thing up on Thursday. Okay.
Sure.
As part of the tutorial, and I'm also going to spend some time if they want on the assignment, okay, problems. If they care to attend, if they do care, let them attend, because no one bothers to attend classes anyway. Okay, they probably rely on the thing, so we don't need to bother either. Okay, so even if one or two attends, that's okay, but we will just record and then upload it. They can view at their own pleasure if they care about it. Whatever. But what we'll do is there will certainly be some assignments and quizzes on this thing will be tested. Okay, I'm just giving you the warning. I don't even have to announce that. So if you care, you can use that. Okay, so let's do that. Okay, Thursday. I mean, the reason I'm doing Thursday is optional, so you don't need to attend at all. Okay, it's optional for you. But from optimism, because it doesn't matter anyway. I mean, even if it's on a regular class, people don't attend. Therefore, we might as well record it at our convenience, and we'll upload it, and you view it or not view it, whatever that you want to do. So that's what I'm going to do. I'm just intimating you. I will send the entire class. I'm saying you did attend. Okay, so I think so. Let's do that for a plan. Yeah.
Yeah, sure.
And I'm willing to discuss the assignment. I don't know. I mean, it's probably the deadline is already over. Okay, maybe you have to give it things. So if they've already done it, maybe I don't even need to discuss it. Okay.
Actually, most of us had issues with the second part.
Well, you're only telling me after I ask you. Okay. So if you had issues, usually a diligent and a thing, you'll have to ask the question before the deadline. Okay.
So they have asked a few questions regarding the first part to me.
Yeah.
They have asked a few questions regarding the first part to me, and I think there was one question regarding the second part.
Oh, okay. So your question is only on the first part. Anyway, so we can spend some time tomorrow, okay, and then get the thing done.
Okay, sure.
Thank you for